T of C of U is equal to C times T of U. So showing that something is a linear transformation is a lot of work. It's often easier to show that something is not a linear transformation if it isn't a linear transformation. Let's look at some examples of things that are not linear transformations. Okay. So show that the following. Are not linear transformations. So find a counterexample. And we're not going to find the domain and find a domain and codomain. Find a counterexample. So, and then I want to find the domain and codomain. So these are not linear transformations, but they still have a domain and codomain. So I want to know what those are. All right. Put a couple of them on the board. I'm going to actually put 3. And then we'll look at some properties here. Okay. Here we go. I have A. Let me just write them on the board. Just a little bit different from what I have, the way I wrote it on the PowerPoint, but it's the same thing. So I have T of X, Y, Z. Okay, I just wrote it in vector form. Is equal to, here I have X squared, I have X plus Y. Now, before we continue, I can actually find the domain and codomain, right? The domain is just where my input is going to be coming from. What's the space that my input is coming from, right? And if you look at this, my input is coming from R3. My input is coming from R3. So my domain, where my input is coming from, is R3. What's my codomain? Where is my output going to? Right, and my output is going to R2. Right? I have 2 coordinates. So my domain is R3, my codomain is R2. Okay. So even if it's not a linear transformation, I can still find the codomain and the domain. Okay. Just looking at where are my inputs coming from? They're coming from R3. Where are my outputs coming from? They're coming from R2. Okay. So codomain and domain. Now, why is this not a linear transformation? Well, some of you guys can see it automatically. You're probably saying it's not a linear transformation because there's a square there. This square is going to stop it from being a linear transformation. When you hear linear, you think of things being something that has it has only powers of 1, right? So in this case, this is a power of 2, so we're not going to get a linear transformation from this, right? Because it's quadratic. And you're absolutely right. That's the case. However, let's actually show that one of these 2 properties breaks, right? Let's show that when we use some numbers, right, or some vectors, right, one of these 2 properties doesn't hold. And then hopefully this will help clear up a couple of things. So let's actually use some real numbers. Let's use numbers here. Let's actually use some numbers. What's the thing you guys think is going to mess us up? It's going to be this x squared, right? So let's pick a vector in which I know that when I square it, I'm going to get something much different from other times. So I'm going to let my x value be, I won't let it be 0 or 1, because 0 squared is still 0, and 1 squared is still 1. Same thing as, so I don't want to do that. So let's just pick a different vector. So let's say x, y, z, let's say, I don't know, let's say 2, 1, and 3. Okay. Now, which vector should we choose, right? I'm going to actually choose this one. Can I choose this one right here? Okay. And I'm going to choose B. Now I could have chosen C. I could have chosen A as well, but I need another vector. I'll let this one be U. I would need a vector V that I need to add together. So I could have used the first option, but let me just use the second one. I'm going to do T of C of U is equal to C times T of U. All right, so I need a C. What's a good C here? Let's not pick C to be equal to 1 or 0. That's not going to help us out here. I'm going to let C be 2 as well. Why not? Okay. So what is 2 times U? Okay, or C times U in this case. And that's going to be 4, 2, and 6. Okay. Now let's see if the left side equals the right side. So I'm going to show this T of C of U equal C of T of U. Question mark. Right? Do they equal each other? And hopefully the answer is no. Right. So T of C of U, that is 4, 2, and 6. Okay, this is C times U. When we plug that in, what do I get here? Going by this rule, I get x squared, which is going to be 16. Right? This is going to be my x squared. And then I have x plus y, right? So when I do 4 plus 2, right? Remember, I'm going by this rule, so I'm essentially using only the first and the second coordinates. So the first and the second coordinate I'm going to add together to give me 6. Okay. Just think of this and just tell me the placeholders. These are just placeholders. X, Y, Z are just placeholders that tell us where each one of these parts are supposed to go in my function. Okay. And what is C times T of U, right? So let's do 2 times T of 2, 1, 3. That'd be 2 times, right? And let's see, hopefully this doesn't work out. I'm keeping my fingers crossed here. So this would be x squared, so 2 squared, which is 4. Then I have 2 plus 1, which is 3, right? I don't do anything with this last component, z. And so when I add and multiply this, I get 8 and 12. Oh no, 8 and 6. Okay. Are these guys the same? And the answer is, no, they're not. They're not the same, not equal. So I know that this is not a linear transformation. Again, like I said before, I could have chosen to use the first part, right? And I think the first part would also have broken, depending on what vectors U and V I picked, right? And you can do that at home yourself to see if the first part breaks as well, right? But I do know that the second rule, the second property does not hold, right? The second property does not hold. So I know that this is not a linear transformation. Okay. Let's look at another one. Okay, let's look at this one. Here, let's do a very simple transformation. T of U, okay, is equal to, actually I'm just going to say T of X is equal to the absolute value of X. T of X is equal to the absolute value of X. Now notice I don't have any brackets around this, right? I don't have any brackets around this. This means that these X is in R, right? So my domain is R, okay? And my codomain, right? What happens when you take the absolute value of a vector? You're also going to be back in R. If I wanted to, I could say it's essentially non-negative numbers, right? I could say my codomain is all negative numbers, but I'm just going to say my codomains are. My range is going to be all non-negative numbers. Can you see that? My range is going to be all non-negative numbers. My codomain, I can say my codomain is just all of R. This just the space that I'm living in this particular situation. Okay, so I just erased my two properties that I said I wasn't going to erase. Let me put them down here. T of u plus v equals T of u plus T of v. And then I have T of c times u is equal to c times T of u. Okay. These are the two properties that have to hold. Now, which one of these properties breaks? Well, both of them break, right? But let's choose the first one this time. Let's choose A, because I chose B last time. There may be a situation where one of them breaks, but the other one doesn't. So you have to be careful about that. But in this case, I think both of them break again. So I want to show that this one also fails, that this is not a linear transformation. Now, how can I do that? Well, I need to pick a u and v, because I'm going to use a in this case. So let's say u is equal to 5, and I'll say v is equal to -3. Okay. A is equal to 5, v is equal to -3. So let's do T of u plus v. Okay. Oh, well, what is u plus v? U plus v is equal to 5 minus 3, that is 2. Okay, so I have T of 2, okay, which is the absolute value of 2. What's the absolute value of 2? It's 2. Okay. I don't need to box that. Okay. Absolute value of 2 is 2. All right, let's do T of u plus v. T of u plus T of v. That's what I want to say. T of 5 plus T of -3. Okay. T of 5 is absolute value of 5. T of -3 is the absolute value of -3. What's the absolute value of 5? Well, it's 5. Absolute value of -3 is 3. So I get 5 plus 3 is 8. Are these guys the same? The answer is no, they are not, right? Again, not equal, not the same. So this is not a linear transformation. Property 1 fails, right? Not linear transformation. Property 1 fails. And one more. I hope you guys are kind of getting this, the idea of what we're doing here. If you get this, it makes it, talking about vector spaces, a little bit easier when we get there. Although I'm doing it in an order that I usually don't do it in. I usually do vector spaces first. But times are weird, times are changing, so we need to adapt with the times. Right? And I think this is the best way, this is the best order to go into this rest of the semester. Okay. Last one. Here it is. This is one that I have on the PowerPoint, and here it is. I'll call it C. And we'll say that T of A is equal to the determinant of A, and A is a 2 by 2 matrix. Although it doesn't have to be. A just has to be a square matrix. But let's just say that it's a 2 by 2 matrix. It has to be a square matrix so that we have a determinant. If we don't have a square matrix, we can't find a determinant. So that's why, so I just made it the smallest square matrix. Well, I could have done a 1 by 1 or 0 by 0, but that's not very interesting. So we have a 2 by 2 matrix. And I want to show that this is not a linear transformation. Let's talk about the domain and the codomain here. What's the domain? Well, if you think about it, where are all my possible inputs coming from? They're coming from the 2 by 2 matrices, right? So my domain is M to 2. Okay. Where's my codomain? What's my codomain? Well, determinants are coming from where? The determinant is going to be a what? What type of output? It's going to be a real number, right? So it's going to, my codomain is going to come from R, right? So all my outputs are going to come from R. I'm going to assume that my 2 by 2 matrices have numerical values, real values. If A, of course, A could have variables in it. A could have complex numbers in it. But I'm going to assume that A is just a regular matrix from the reals. That's not specified here, but just to keep it kind of simple, that's what we're going to say. So why is this not a linear transformation? Let's think about that, right? Well, if we look at this, let's say, all right, this one's a little bit different from the last one that we dealt with. It would be nice to show that one of these properties doesn't hold, right? One of these properties is no good. Now, which one can we choose? That one's, it's not obvious, but there's one that works here. So let me kind of guide you guys through it. I need to show that when I add two matrices together, right, and then take this transformation, I don't get something that when I take the transformation of each one of those matrices separately and add them together, I get something totally different. That's what I want to show. I want to show that I get totally different things. So let's pick a matrix. Let me kind of guide you through it. So I have 1, 0, 0, 1. Okay. What's the determinant of 1, 0, 0, 1? Well, the determinant of this is 1, right? Now, if I were to add it to another matrix, right? Let's say I add it to the matrix, I don't know. What's a good one? What can I use here? Maybe if I use -1, 0, 0, -1. What's the determinant of this matrix? The determinant of this matrix is also what? 1. Okay? So the determinant of this matrix is 1, the determinant of this matrix is 1. What happens when I add these two matrices together? Okay, 0, 0, 0, 0. What's the determinant of this matrix? It's 0. Okay. Now, can you kind of see which one is going to fail here? Well, let's look at it. Let's see if we can put it all together now. T of u plus v. It's going to be T of 0, 0, 0, 0. The determinant of this matrix is going to be 0. Well, what's T of u plus T of v? T of 1, 0, 0, 1 plus T of -1, 0, 0, -1. What is that going to be? Determine this one's 1 plus 1, that gives me 2. Are these equal to each other? Are they the same? Are they equal? Absolutely not. Not equal. Absolutely not equal. So that means that this is not a linear transformation. Property 1 fails, right? Okay, property 1 fails. If I did that correctly, which I hope I did. So we just shown 3 examples of how of finding essentially a counterexample, giving an example in which the property that shows that this is not a linear transformation. So I want you guys to know is that there's multiple ways that these things were not linear transformations, right? Transformations. This one's a little bit obvious because of that square. This was not as obvious, but because of those absolute values, it kind of screwed us up. And this one's not obvious at all because we're dealing with the determinant. It's kind of like a black box sometimes, it feels like, when we deal with the determinant. All right, so let's jump topics. Well, not topics, but let's just talk about something else. Let's talk about properties of linear transformations. Properties of linear transformations. Properties of linear transformations. Okay. And there's really just two properties I want to put on the board. The first property is that the transformation of the zero vector is the zero vector. Now we have to be careful here because we need to make sure that we understand what we mean. Now here, this is the transformation of the zero vector in V. In V is equal to the zero vector in W. Okay? For instance, the zero vector, if suppose V is R2 and W is R3, right? The zero vector in R2 is the 2 tuple 0, 0. The zero vector in R3 is the 3 tuple 0, 0, 0. But no matter what, the transformation of the zero vector is going to be the zero vector in that particular space that we're in. Okay? That's one of those properties. That's very cool. So 0 always maps to 0. It just might not look like the 0 that you're used to. 2. If V is equal to the linear combination of vectors v1, v2 through vn,